Everything you have ever seen is less than 5% of the universe. The rest is an invisible presence known as dark matter, the cosmos's dominant yet ghostly ingredient. By the end of this, you will have a complete tour of the 30 most compelling explanations for what it could be. We will explore if it is made of undiscovered particles, if it is a sign that gravity itself is broken, or if the answer is something far stranger. What single idea about our universe most challenges what you think is possible? For decades, one candidate has stood at the forefront of the hunt. They are called WIMP, or weakly interacting massive particles. The name itself tells you their story. They are thought to be heavy, giving them the gravitational pull we observe, and they are weakly interacting, meaning they mostly ignore normal matter and light passing through our world like ghosts. This elegant idea did not just appear from nowhere. It emerged beautifully from a highly theoretical framework known as supersymmetry, which proposes a hidden, mirrored partner for every known particle in the universe. Within that elegant mathematical structure, a perfect dark matter candidate naturally appeared. This theoretical promise made WIMP the favorite explanation for a generation of scientists. The search for them became a global scientific epic. To shield these incredibly delicate experiments from the constant cosmic rain of ordinary particles, physicists built laboratories deep underground. Imagine facilities housed in old mines or beneath mountains, where over a mile of solid rock acts as a natural filter. There, in the profound silence and darkness, scientists wait for the telltale bump, the tiny flash of heat or light that would signal a WIMP has finally, after billions of years, bumped into an atom of a normal substance. Yet, after decades of searching with ever more sensitive detectors, that definitive signal has not come. The profound quiet in those deep places is itself a result. So why does the WIMP hypothesis remain so compelling? Because it solves two puzzles at once. It provides the missing mass of the universe, and it does so with a particle that fits perfectly into our most ambitious theories of how reality works at its most fundamental level. It is a solution that is almost too beautiful to abandon. But as the silence from those deep underground labs grew louder, another contender began to shine. It is a particle born from a completely different cosmic puzzle. Meet the Axion. While WIMP were imagined as heavyweights, Axions are the featherweights of the dark matter world. Hypothetical particles so incredibly light that trillions of them could be passing through your hand every single second without you ever noticing. Their story does not even start with dark matter. Physicists first dreamed them up to solve a nagging mystery in the strong nuclear force, the glue that holds the cores of atoms together. The math said this force should violate a fundamental symmetry of nature, making the universe look different if you swapped left for right and matter for antimatter. But in reality, it does not. The Axion was the elegant fix, a new field that would quietly correct this cosmic accounting error. And in doing so, it would fill the universe with these ghostly, wave-like particles. Think of the early cosmos not as a place of solid things, but as a sea of shifting energy fields. As the universe cooled, one of these fields began to oscillate, to ripple in a specific, universal rhythm. Every single oscillation would have produced an action. This process could have been so prolific that these waves, these ripples in reality, froze into a cosmic background sea, collectively possessing all the gravitational weight we now call dark matter. So how do you hunt for something so ethereal? You build a cosmic radio. Experiments like the Axion Dark Matter Experiment, or ADMX, are essentially giant supercooled tuners. They create a powerful magnetic field, hoping that an action passing through will very rarely convert into a faint microwave photon. The experiment then slowly, meticulously scans through millions of possible frequencies, listening for that one specific note in the cosmic static. It is a search for a single, ghostly voice in a universe of noise. Perhaps the answer is not something new, but something ancient and hidden in plain sight. What if dark matter is not an exotic particle at all, but simply ordinary matter that has collapsed into dark, massive objects littering the cosmos? This is the premise of the third theory, MACHO, an acronym for Massive Astrophysical Compact Halo Object. The idea is elegantly simple. Imagine black holes left over from the earliest universe, or vast swarms of neutron stars, brown dwarfs, and failed stars too dim to see. These would be made of the same protons and neutrons that build our world, but their sheer darkness and mass could provide the gravitational glue that holds galaxies together. They would be the ultimate cosmic ghosts, made of familiar stuff but invisible to our telescopes. To find them, astronomers did not go underground. They looked toward the crowded heart of our galaxy. Their tool was a prediction from Einstein's theory of relativity, a phenomenon called gravitational microlensing. The concept is breathtaking. If a dark, massive object like a black hole passes directly between Earth and a distant star, its gravity will act like a lens, bending and focusing the star's light. From our viewpoint, that faraway star would temporarily brighten, then fade, as the invisible lens moves across our line of sight. It is a ghost taking a fleeting silhouette against a distant light. For years, teams like the MACHO project and EROS meticulously monitored millions of stars in the Large Magellanic Cloud, a small satellite galaxy of our Milky Way, watching for these telltale flashes. They found them. The sky was indeed flickering with these gravitational mirages, proving that such dark, massive objects do exist, but the final count was devastatingly low. There were not nearly enough of these events to account for the immense gravitational pull we observe. These ordinary dark objects, these MACHO, could only make up a tiny fraction, less than a handful of percent, of the dark matter needed. The universe had seemingly ruled out a simple answer. The missing mass could not be made of the same stuff we are. It had to be something fundamentally different, something that does not interact with light at all. This failure was a profound turning point. It forced science to accept that the true nature of dark matter is not just dark, but truly alien. The quiet failure of MACHO forced physicists to look deeper into the subatomic world, to particles we already know exist but barely understand. We are constantly being showered by trillions of nearly massless particles called neutrinos, born in the hearts of stars and cosmic explosions. They are famously aloof, passing through entire planets with almost no interaction. But what if dark matter is a secret, heavier relative of these cosmic phantoms? This brings us to the fourth theory, the sterile neutrino. Imagine a neutrino that has taken its reclusive nature to the absolute extreme. While ordinary neutrinos are governed by the weak nuclear force, allowing for a tiny chance of interaction, a sterile neutrino would feel only gravity. It would be completely deaf to every other force in the universe, a true shadow particle. Its existence would be inferred solely by its gravitational weight. The motivation for such a ghost is surprisingly practical. For decades, physicists have been puzzled by a strange signal from the cosmos, a faint, specific spike of X-ray energy seen emanating from galaxy clusters and other massive structures. This emission line has no clear explanation with known physics, but it perfectly matches the energy that would be released if a sterile neutrino, after drifting for billions of years, spontaneously decayed into an ordinary, lighter neutrino. In that single, rare event, the invisible would briefly become visible, leaving this X-ray fingerprint. The idea is tantalizing because it offers a two-for-one deal. It provides a particle that could be the dark matter, and it simultaneously explains an awkward, unexplained astronomical observation. Yet the sterile neutrino remains deeply controversial. Despite dedicated searches, that specific X-ray signal has been difficult to confirm in other objects, and experiments designed to catch neutrinos changing their type have so far found no evidence for this heavy, sterile cousin. The debate rages on. Is that X-ray line the first glimpse of the universe's dominant material, or is it just an intriguing cosmic mirage? While sterile neutrinos remain elusive, another theory points to gravitational monsters born from the universe's first chaotic moments. Imagine black holes that did not form from the death of massive stars, but instead coalesced from the raw, seething energy of the Big Bang itself. These are primordial black holes, and they could be the dark matter we have been searching for. Unlike their stellar cousins, which have masses many times that of our Sun, primordial black holes could be almost any size. Some might be as small as an atom, yet contain the mass of a mountain. Others could be the size of a large asteroid with the gravitational pull to hold a galaxy together. They would be pure, unadulterated gravity, cloaked by an event horizon from the very dawn of time. For decades, this idea was on the fringes of cosmology, but then a new window onto the universe opened. The detection of gravitational waves, the ripples in space-time from colossal cosmic collisions, brought this theory roaring back into the spotlight. When the LIGO Observatory heard the space-time shaking chirp of two black holes merging, astronomers were stunned by their mass. They were heavier than expected for black holes formed from dying stars. Could these instead be primordial black holes, ancient relics from the beginning of everything, finally finding each other in the dark? This discovery sent a jolt of excitement through the scientific community. It was a hint, not proof, but it was enough to revive a fascinating question. How could we find something that emits no light and could be almost anywhere? The hunt relies on their gravity. A small, dense primordial black hole passing near a star would subtly distort its light through gravitational microlensing, just as the MACHO searchers looked for. But if these black holes are either very small or very large, they could have evaded those earlier surveys. The future of this search now lies with a new generation of observatories. The Vera Rubin Observatory, with its camera that can photograph the entire visible sky every few nights, will watch for telltale flickers across the heavens. Meanwhile, pulsar timing arrays, which use the incredibly regular pulses from dead stars as cosmic metronomes, could detect the subtle space-time wobble caused by a primordial black hole drifting through our galaxy. We are on the verge of either finding an entire hidden population of ancient black holes or finally closing the book on this profound possibility. What if dark matter is not completely isolated but has a social life of its own? This is the radical proposal of self-interacting dark matter, or SIDM. The standard model of cold dark matter imagines these particles as cosmic hermits, drifting through the universe and feeling only the pull of gravity, never bumping into one another. But what if they do interact? What if they feel a new, unknown force that allows them to scatter off each other, to exchange energy, much like billiard balls colliding on a table? This single change to the rules of the game could solve one of the most persistent mysteries in modern cosmology. For years, supercomputer simulations of the universe, based on the standard cold dark matter model, have predicted that galaxies should have incredibly dense centers. They forecast a sharp peak or a cusp of dark matter at their very core. Yet when astronomers actually measure the distribution of matter in dwarf galaxies, they find something completely different. Instead of a steep cusp, they see a flat, constant density core. It is as if the dark matter has been smoothed out, as if something has been stirring the pot in the heart of these galaxies. Self-interacting dark matter provides an elegant mechanism for this smoothing. Picture a crowded dance floor in the center of a young galaxy. In the standard model, the dark matter particles simply orbit, never touching, piling up into a dense, sharp peak. But in the SIDM model, they can collide. When two particles scatter, they transfer energy. The faster-moving particles can get a boost and migrate outward, while the slower ones sink inward. Over billions of years, this continuous, gentle shuffling erases the sharp central cusp and creates the smooth, flat core that we actually observe. It is a cosmic relaxation process driven by dark matter's own secret interactions. This idea does not just fix the cusp core problem. It also addresses why some galaxies seem to have fewer small satellite galaxies orbiting them than the simulations predict. Those energetic collisions could have gently evaporated the smallest, most fragile dark matter clumps before they ever had a chance to form stars. So the silence in our skies, the missing dwarf galaxies, could be another echo of dark matter's hidden social life. We are left with a profound question. Is the universe's dominant substance a collection of solitary ghosts, or is it a bustling, interactive community, governed by rules we are only just beginning to guess? Sometimes the solution to a massive problem is not to find something bigger, but to look for something almost impossibly small. This leads us to a theory that reimagines the fabric of dark matter itself. It is called fuzzy dark matter, and it proposes that the universe's missing mass is not made of heavy particles, but of ones so incredibly light they defy our everyday intuition. A single such particle would have a mass billions of trillions of times lighter than an electron. At this minute scale, the rules of the quantum world take over in a dramatic way. The particle's quantum wavelength, the fundamental fuzziness of its position, becomes enormous, stretching not across an atom but across an entire galaxy. Instead of a swarm of discrete dots, dark matter becomes a continuous, rippling wave, a coherent cosmic fog that fills the cosmos. This single shift in perspective from a particle to a wave solves one of the most puzzling mismatches in modern cosmology. Supercomputer simulations based on traditional heavy dark matter predict that our Milky Way should be surrounded by many hundreds of small, dark satellite galaxies. Yet when we look, we only see a few dozen. This is known as the missing satellites problem. Fuzzy dark matter offers an elegant solution. In this model, the incredibly long wavelength of the dark matter particles creates a natural size limit for the smallest cosmic structures. Think of it like trying to form a tiny, sharp droplet from a substance that has the consistency of a thick, vibrating jelly. The quantum waves resist being squeezed into very small clumps. They smooth everything out, so while large galaxies can still form, the vast number of tiny dark matter halos, the potential cradles for small satellite galaxies, simply never get a chance to coalesce. The cosmic fog prevents the universe from becoming too clumpy on small scales. The implications are profound. If this theory is correct, dark matter is not a collection of individual entities you could, in principle, count. It is a single, pervasive field humming with a specific energy, its gentle oscillations providing the gravitational scaffolding for everything we see. This would mean that the dominant substance in the universe is fundamentally wave-like, a quantum phenomenon playing out on a truly cosmic scale. It transforms the hunt from searching for a ghostly particle to listening for the specific tone of this background hum. Astronomers are now searching for the unique signatures of this model in the faint, ancient light from the first galaxies, and in the delicate patterns of how stars move within dwarf galaxies. They are looking for the subtle smoothing effect that would be the unmistakable fingerprint of a universe built not on dark particles, but on a dark and fuzzy wave. But what if we have been asking the wrong question all along? Every theory so far has accepted one fundamental premise, that our understanding of gravity is perfect. What if that is the flaw in our cosmic logic? This brings us to the most radical alternative on our list, a theory that dares to suggest there is no dark matter at all. It is called modified Newtonian dynamics, or MOND. The proposal is breathtakingly simple yet profound. Perhaps gravity does not behave exactly as Newton or Einstein described when it becomes incredibly weak, in the outer reaches of galaxies where stars move through a near-perfect vacuum. In these quiet, dark places, the acceleration from gravity is so minuscule it is almost immeasurable. MOND proposes that in this specific regime, the force of gravity strengthens slightly, it gets a tiny boost. This single modification to the laws of physics was first proposed by physicist Mordechai Milgrom in the early 1980s to solve a single, glaring problem, the galaxy rotation curve. You will recall that stars on the outer edges of spiral galaxies were moving far too quickly. Dark matter explained this by adding an invisible halo of mass to provide extra gravitational pull. MOND achieves the same result by changing the rules of the pull itself. It predicts that at these fantastically low accelerations, gravity follows a new set of rules, causing the orbital speeds of stars to flatten out, perfectly matching what astronomers observe without a single particle of dark matter. The success was startling. For spiral galaxies alone, MOND is a master key, fitting the data with remarkable precision. It solved the problem it was designed to solve with an elegance that particle-based theories struggle to match. But a theory of the universe must work everywhere, not just in one place, and this is where MOND faces its greatest trials. When we zoom out from individual galaxies to the vast scale of galaxy clusters, immense gatherings of thousands of galaxies, the picture becomes murky. These clusters are filled with superheated gas that glows brightly in X-rays. The mass of the visible galaxies and this hot gas is not nearly enough to hold the cluster together with standard gravity. They should fly apart. Dark matter models solve this by adding a massive, invisible halo to the entire cluster. MOND, however, still falls short. It requires some additional, unseen matter to explain the gravitational strength of these clusters, though far less than the standard model demands. This has led to hybrid ideas, suggesting that maybe MOND is correct, but there is also some form of hot, non-particle dark matter, like sterile neutrinos, a compromise that purists on both sides find unsatisfying. The most significant challenge for MOND, however, comes from a cosmic snapshot, the bullet cluster. This is a system of two clusters that have violently collided. Observations show that the bulk of the mass, mapped through gravitational lensing, has become separated from the visible gas. It is as if two ghosts have passed through each other, leaving the normal matter behind. This is exactly what you would expect if dark matter were a collisionless substance, but it is a profound puzzle for MOND, which ties gravity directly to the visible mass. How can the gravity be where the stars are not? Proponents of MOND have developed complex extensions to try and explain this, but for many, it remains the theory's greatest hurdle. So we are left with a cosmic standoff. Is it more likely that the universe is filled with a mysterious, invisible substance that we cannot touch or see, or that our understanding of gravity itself, a force we have studied for centuries, is subtly incomplete in the deep quiet of interstellar space? The answer will redefine physics. Perhaps the truth lies not in choosing a side, but in weaving the most compelling ideas together. This brings us to a truly sophisticated proposal: superfluid dark matter. Imagine if the ghostly substance that fills galaxies is not a collection of individual particles, but a single, coherent quantum liquid. In the vast, cold emptiness between galaxies, this dark matter would behave just like the standard, collisionless cold dark matter we have discussed. It would form the cosmic scaffolding for the large-scale structure of the universe. But when it falls into the gravitational well of a galaxy, something extraordinary happens. The density becomes high enough and the temperature low enough for this sea of particles to undergo a phase transition, condensing into a superfluid. A superfluid is a state of matter with zero viscosity. It flows without friction, and it can create strange quantum effects on a macroscopic scale. In this model, the dark matter superfluid fills the entire galaxy. And within this superfluid, collective vibrations arise, ripples known as phonons. These phonons are the key to everything. They mediate a new, long-range force that acts on the normal, baryonic matter, the stars and gas we can see. This extra force is not gravity itself, but an additional pull that emerges only within the superfluid regions of galaxies, and it is designed to perfectly replicate the effects of modified Newtonian dynamics. In the outskirts of a spiral galaxy where gravitational accelerations are tiny, this phonon force kicks in, providing the extra pull that makes stars orbit faster without the need for a halo of invisible mass. It gives you the precise success of MOND where it works best, right inside galaxies. Yet, on the scale of galaxy clusters, or in the case of the bullet cluster, the model switches back to its other identity. In these environments, the dark matter may be too hot or too diffuse to form a coherent superfluid, so it behaves like standard collisionless particles. This explains why the gravitational lensing in the bullet cluster appears separated from the visible gas. The dark matter simply passed through the collision, just as the standard model predicts. This theory is a brilliant attempt to have it both ways. It preserves the overwhelming success of cold dark matter for the entire cosmos, while also capturing the undeniable elegance of MOND explanation for galaxy rotations. It proposes that dark matter is not simple but complex, capable of existing in different phases with dramatically different behaviors. The hunt for this idea is now a hunt for the unique signatures of a quantum fluid permeating our own galaxy. Could the subtle movements of stars reveal the gentle push and pull of phonons in a dark superfluid sea? We are searching for the evidence of a substance that is both a particle and a wave, a cosmic scaffolding and a dynamic, intelligent fluid. The creation of dark matter might be the universe's oldest and most enduring echo. To find its origin, we must journey back to the very first moments of time, when the cosmos was an immeasurably hot, dense soup of energy and nascent particles. In that primordial forge, every kind of particle, including the hypothetical constituents of dark matter, were constantly colliding, annihilating, and being recreated from the intense heat. They were in a state of thermal equilibrium, locked in a frenzied dance with everything else, but the universe was expanding and cooling at a phenomenal rate. As the temperature plummeted, a critical threshold was crossed. The energy of the particle soup dropped below what was needed to continuously recreate a specific type of dark matter particle. In an instant, the frenetic collisions and recreations stopped. The dark matter particles could no longer find partners to annihilate with, and they simply froze out. Their numbers became fixed, a relic population left drifting in the expanding cosmos. This is the powerful concept of thermal relic dark matter, a fossil record etched into the fabric of space itself from a time before the first stars. The most stunning example of this is the so-called WIMP miracle. When theorists calculated the properties of a hypothetical weakly interacting massive particle, they found something that sent chills through the scientific community. For a particle with a mass about 100 times that of a proton and an interaction strength governed by the weak nuclear force, the predicted leftover abundance from this freeze-out process matches the observed density of dark matter in the universe almost perfectly. It is a numerical coincidence so precise and so compelling it feels less like a calculation and more like a revelation. The universe seemed to be whispering a hint, suggesting that the answer had been woven into the laws of physics all along. This single, elegant alignment has driven decades of experimental effort, from deep underground labs to powerful particle colliders. It is the hope that the dominant substance in the cosmos is not a random anomaly, but a natural and inevitable consequence of the universe's fiery birth, a thermal ghost from the dawn of everything. The profound silence in our detectors might be telling us that dark matter is not just a thermal relic, but a cosmic mirror. We live in a universe made overwhelmingly of matter, with antimatter almost entirely absent. This is one of physics' deepest mysteries. Why is there something rather than nothing? Asymmetric dark matter proposes a breathtakingly elegant answer. It suggests that the very same cosmic imbalance that filled the cosmos with stars and planets also filled it with invisible mass. In this theory, dark matter is not a neutral bystander. It is its own antiparticle, a type of matter known as a Majorana particle. This means if two dark matter particles collide, they can annihilate each other in a flash of energy, just like matter and antimatter. In the searing heat of the Big Bang, dark matter and its antiparticle counterpart should have been created in equal amounts. If that had happened, they would have completely annihilated away, leaving behind a universe with no dark matter at all. The fact that we are surrounded by it is the crucial clue. Something must have tipped the scales. A subtle instability in the laws of physics must have favored the creation of dark matter particles over their antiparticles by just 1 part in a billion. This tiny preferential production left behind a vast residual population of dark matter, the gravitational backbone for everything that followed. The beauty of this idea is its connection to our own existence. The visible universe exists because of a similar asymmetry, where a slight excess of quarks over antiquarks led to all the atoms we see. Asymmetric dark matter weaves these two stories into one. It posits that the process which generated the matter asymmetry also, through a hidden link, generated the dark matter asymmetry. They are two sides of the same primordial coin. This transforms the hunt. We are no longer just searching for a ghostly particle. We are looking for the signature of a fundamental cosmic preference, a bias written into the laws of nature that made our very reality possible. Could the dominant substance in the cosmos be the silent sibling of the atoms that build our world? The silence in our detectors might not mean dark matter is simple, but that it is part of an entire hidden reality. Imagine a parallel universe of particles and forces operating right alongside our own, completely invisible and undetectable except for a single, momentous leak: gravity. This is the theory of a dark sector, and at its heart could be a particle known as the dark photon. Just as the familiar photon is the carrier of the electromagnetic force in our world, governing light and chemistry, the dark photon would be the carrier of a new, hidden force within the dark sector. It would allow dark matter particles to interact with each other, to attract or repel, to possibly even form complex dark atoms and dark molecules, all without ever touching the world of light. This is not just one new particle, it is the potential for an entire shadow cosmos living within our own. The only conceivable bridge between our world and this dark sector would be through the dark photon itself. In rare and highly specific circumstances, a standard model photon, a particle of light, could oscillate or mix with a dark photon. This would be the only whisper, the only hint of this vast, complex civilization of particles operating in the shadows. The hunt for this effect is one of the most delicate in modern physics. Experiments use powerful magnetic fields and highly sensitive detectors, hoping to see a beam of ordinary light lose a tiny fraction of its photons as they momentarily transform into their dark counterparts and vanish. Other searches look for the reverse, where a dark photon might decay into a faint, unexpected pair of an electron and its antimatter partner, a fleeting spark from the darkness. The implications are staggering. If a dark sector exists, then dark matter is not a single, lonely ghost. It is a citizen of a bustling, hidden metropolis with its own laws and interactions. The dominance of dark matter in the universe would no longer be a mystery of absence, but a simple consequence of an entire parallel reality whose gravitational shadow is the only thing we can feel. We are left wondering if we are the odd ones out, living in a luminous but insignificant corner of a cosmos that is mostly dark and teeming with its own unseen forms of complexity. Deep within the elegant equations of supersymmetry lies another ghost, a particle born from the marriage of the two most powerful ideas in physics. This is the gravitino. If the universe is truly supersymmetric, then every known particle has a hidden, heavier twin. The photon has the photino, the electron has the selectron. And the graviton, the hypothetical messenger of the gravitational force, would have its own superpartner, the gravitino. It is a particle of profound significance, theoretically bridging the quantum world with the force that shapes the cosmos. In many models, the Gravitino is staggeringly heavy, perhaps even the heaviest of all the superpartners. This immense mass would make it incredibly sluggish in the modern universe, a perfect candidate for the gravitational glue we call dark matter. But this theoretical beauty comes with a devastating cosmic problem, one of speed. In the searing heat of the Big Bang, Gravitinos would have been created with ferocious energy, moving at velocities approaching the speed of light. This is what cosmologists call hot dark matter, and we know with great certainty that hot dark matter cannot build the universe we see. If dark matter particles move too fast, they simply smooth out the cosmos before any structures can form. They would wash away the delicate gravitational seeds that eventually grew into galaxies and clusters. A universe dominated by hot dark matter would be a vast, featureless sea with no stars and no planets. Our existence is proof that dark matter must be cold, or at most lukewarm, moving slowly enough to clump together and create the intricate cosmic web. So how could the Gravitino, born in a fiery sprint, have slowed down enough to become the cold dark matter we need? Physicists have been forced to imagine exotic scenarios in the early universe where other, unknown fields or particles interacted with the Gravitinos, sapping their energy in a process known as thermal inflation. It is a theoretical fix, a way to make the numbers work, but it lacks the clean, predictive power of the WIMP miracle. The Gravitino remains a compelling yet deeply challenging candidate, a reminder that even our most beautiful mathematical structures must ultimately bow to the evidence written in the stars. Our universe might have more rooms than we can perceive. Step beyond the 3 dimensions of everyday experience into a realm where hidden, curled-up dimensions exist at a scale so tiny they evade all detection. Within this extraordinary framework, dark matter could be nothing more than an echo, a vibration in these unseen directions. These are Kaluza-Klein particles, named for the physicists who first dared to blend gravity and electromagnetism by proposing a 5th dimension. In this view, what appears to us as a massive particle is actually a much lighter entity moving in a tight circle through a dimension we cannot access. Its momentum in that hidden space manifests as mass in our own, a cosmic sleight of hand where geometry creates substance. This idea is not merely a mathematical curiosity. It emerges naturally from the most ambitious attempt to unify all forces, string theory. To make string theory work, the universe requires more than 3 spatial dimensions, often 7 extra ones, all compactified or scrunched up into a fantastically small size. Each of these hidden dimensions would have its own set of vibrational modes, its own notes. A Kaluza-Klein particle is simply one of these higher notes, a resonance from the compact dimensions that carries mass and gravity into our world, while remaining deaf to light and other forces. So how could we ever detect a ghost from a hidden dimension? The key is energy. If we could harness enough power, perhaps in a next-generation particle collider, we might be able to excite matter enough to make it jump into one of these compact directions. The signature would be dramatic. We would see a particle appear in our detector, but its properties, particularly its mass, would not match any known particle. It would be the telltale sign of a Kaluza-Klein state, a direct glimpse into the geometric underpinnings of reality. Alternatively, some of the most energetic particles in the cosmos, ultra-high energy cosmic rays, might already be creating these particles when they slam into our atmosphere. Experiments like the Pierre-Auger Observatory are sifting through these rare events, looking for anomalies that could be the fingerprint of extra-dimensional decay. The search is for a shadow cast by the very shape of space itself. Some of the most promising dark matter candidates are also the most elusive, but what if the answer is not a fundamental particle at all? What if it is a cosmic fossil, a stable and massive object that formed when the universe was just a fraction of a second old? This brings us to the fascinating theory of cue balls. Imagine the primordial cosmos not as a smooth soup, but as a seething, chaotic froth of energy fields. In certain theories, these fields can become tangled and knotted, collapsing into stable, soliton-like objects. A cue ball is precisely that, a coherent blob or bubble of a scalar field, a stable knot of energy that could be almost any size, from smaller than a proton to larger than a star. It is not made of particles in the conventional sense, but is instead a single, giant quantum object, a macroscopic entity that carries a specific and conserved charge. This charge, denoted by the letter Q, is what gives the cue ball its incredible stability. It cannot decay into smaller particles because that would violate the conservation of this fundamental quantity. It is a cosmic tumor of sorts, a benign and stable lump in the fabric of reality that has persisted for billions of years. The sheer range of possible masses is staggering. A cue ball with the mass of an asteroid could easily pass through our planet, its gravitational pull the only sign of its presence. Because it is not a black hole, it would not tear space-time apart with a fierce event horizon, yet its concentrated mass would make it a potent source of gravity. This makes cue balls a unique candidate, sitting in a strange middle ground between elementary particles and massive astrophysical objects. Their interaction with normal matter would be incredibly rare and weak. A charged cue ball might interact electromagnetically, leaving a faint trail of ionization, but a neutral one would be almost completely invisible, felt only by its gravitational influence. The hunt for these objects is as creative as the theory itself. Some experiments search for the seismic vibrations or unusual heat signatures that a transiting cue ball might leave deep underground. Others look to the skies, monitoring large arrays of detectors for the simultaneous flashes of light that would occur if a single, massive cue ball passed through the atmosphere and interacted with multiple atoms at once. The existence of cue balls would mean that dark matter is not a uniform sea of identical particles, but a collection of individual, exotic relics, each a frozen moment from the universe's most violent and creative phase. There is a symmetry to the universe so profound it feels almost artistic. For every particle of matter we know, there could be a perfect mirror image, a shadow twin made from its own unique set of mirror atoms. This is the theory of mirror matter, and it proposes that dark matter is not an exotic particle but a complete, parallel universe identical to our own, interwoven with the space we inhabit yet forever separate. In this breathtaking vision, every star in our sky could have a dark twin, every planet a silent, invisible counterpart, and the potential for mirror life, a whole other biology of shadow, becomes a staggering possibility. The two sectors, the ordinary and the mirror, would have been born together in the Big Bang, governed by the same laws of physics, but they would interact with each other in only one way, through the gentle, universal tug of gravity. This elegant concept solves one of the most puzzling numerical coincidences in all of cosmology. Why is the amount of dark matter in the universe so similar to the amount of ordinary matter? In most particle theories, this ratio is a random, unexplained number, but in the mirror matter hypothesis, it is natural. The two sectors are symmetric, two sides of the same cosmic coin, so it makes perfect sense that they would have been created in nearly equal amounts. The slight imbalance we observe could be the result of a tiny breaking of that perfect symmetry in the first moments of time, a faint crack in the cosmic mirror that allowed our luminous world to become distinct from its dark twin. Think of our reality as one sheet of paper and the mirror world as another, pressed tightly together. We can never see or touch the writing on the other sheet, but if you place a heavy object on one, both pages will bend. That bending is gravity, the only language shared between these two parallel realities. This means mirror photons would be invisible to our eyes, mirror electrons would ignore our magnetic fields, and a mirror person could walk right through you with neither of you ever knowing. The hunt for this ghostly twin universe involves looking for the subtle gravitational whispers it leaves behind. Astronomers search for tiny, unexplained gravitational anomalies in the orbits of stars or the bending of light from distant quasars. the potential signature of a dense mirror object passing through our neighborhood. Other searches are more direct, attempting to measure the incredibly faint forces that might arise if an ordinary neutron and a mirror neutron could somehow oscillate into one another, a process that would make neutrons seemingly disappear and reappear in a sealed container. The implications are as humbling as they are awe-inspiring. The cosmos would be doubly rich, filled with constellations we can never see and civilizations we can never contact, all bound together by the silent, invisible threads of gravity. Perhaps the most minimal answer is also the most profound. Dark matter might interact with our world through one channel and one channel only, the quantum whisper of gravity itself. This is the hypothesis of Planckian interacting dark matter. Forget new forces or hidden sectors. This idea strips the concept down to its bare essentials. It proposes that the only conversation between dark matter and ordinary matter happens through the exchange of gravitons, the hypothetical, fundamental packets of the gravitational field. In the quantum world, forces are mediated by these messenger particles. Photons carry the electromagnetic force, gluons carry the strong nuclear force, and theoretically, gravitons carry gravity. In this model, a dark matter particle floating through Earth would only ever make its presence known by exchanging a graviton with a proton or an electron in an atom. The probability of this event is almost zero. It is so vanishingly rare that it makes the search for WIMP look straightforward. This is because gravity is, by an almost unimaginable margin, the weakest force in the universe. The gravitational attraction between two protons is about 10 to the 36 times weaker than their electromagnetic repulsion. To put that number into perspective, it is like comparing the strength of a single person to the combined pull of every star in a trillion galaxies. Relying on graviton exchange for detection means that dark matter is not just dark, it is almost perfectly transparent. This minimalist approach is both elegant and deeply challenging. It represents a philosophical endpoint, asking what is the least we must assume to explain the gravitational effects we see. The answer is nothing more than particles that feel gravity and nothing else. But how could we ever hope to find something that refuses to speak any language except the faintest one in nature? The hunt pushes experimental physics to its absolute limits. It involves looking for minuscule vibrations in crystalline materials cooled to a fraction of a degree above absolute zero, sensors so sensitive they could hear a pin drop on the moon. Even then, the signal would be a statistical ghost, a tiny excess of energy that could just as easily be background noise. This theory forces us to confront a haunting possibility. The dominant substance in the universe may be fundamentally and permanently invisible to any form of direct detection we can ever devise. Its existence known only by the silent, persistent bending of light and the graceful spin of galaxies. The universe may be built with layers of reality we cannot perceive, like a castle with secret rooms hidden behind its main walls. This is the enchanting premise of hidden valley models, where dark matter is not just a single particle but an entire civilization of them, living in a secluded sector of physics. In this view, our familiar world of atoms, light, and forces is just one valley. Another valley, entirely separate, exists in a parallel space of existence. The particles in this hidden valley talk only to each other, governed by their own dark forces, forming dark atoms, dark molecules, and even dark chemistry, all completely invisible to our most powerful instruments. The only conceivable border crossing between our world and this hidden one is through a portal, a hypothetical particle that can travel between the valleys. One of the most promising portals is the dark photon, a hidden twin to the particle of light. Through this single, incredibly narrow bridge, a tiny amount of energy or information might occasionally leak. This setup elegantly explains one of the great frustrations in the hunt for dark matter. Our most sensitive direct detection experiments buried deep underground have found nothing. In the hidden valley paradigm, this silence is exactly what you would expect. The particles in the secluded sector simply do not bump into our protons and neutrons. They are not just dark, they are citizens of another country with very strict border controls. Yet there might be another way to see them. What if these hidden particles are not completely stable? What if they can annihilate each other? Imagine two dark matter particles from the hidden sector colliding. They would not just vanish. According to Einstein's famous equation, their mass must be converted into something else. In their own valley, they could annihilate into a shower of other hidden particles like dark electrons or dark photons, but that energy has to go somewhere. Through the portal of the dark photon, that hidden energy could be converted into a burst of familiar, high-energy gamma rays in our own world. We would see a mysterious, unexplained fountain of light pouring from the center of our galaxy or from dense dark matter halos with no visible object to account for it. This is the hope of indirect detection. Experiments like the Fermi Gamma Ray Space Telescope are constantly mapping the sky, searching for these exact signatures, these ghostly beacons that could be the final shout of dark matter annihilating in its hidden realm. The hidden valley theory turns the cosmos into a place of immense and hidden activity. The emptiness of space is an illusion. It may be teeming with the complex, invisible dramas of an entire other reality, whose only echo in our world is a faint, high-energy light we are just learning how to read. While WIMP whisper of elegant connections to our visible world, another theory proposes a dark matter that is fiercely independent. These are strongly interacting massive particles, or SIMP. The name is the entire philosophy. Instead of being weakly interacting ghosts, SIMP are social butterflies within their own hidden realm. They feel a powerful new dark force, causing them to constantly collide and interact with each other. In this model, the dark sector is not a collection of lonely drifters, but a bustling, self-contained metropolis. The creation of this dark matter involved a completely different kind of party. For WIMP, the relic abundance was set by their annihilation with their own antiparticles into ordinary matter. But for SIMP, the key process happens entirely within the dark sector. Think of it as a cosmic game of musical chairs where only dark matter particles are playing. The most important reaction is a 3-to-2 interaction. Picture three SIMP coming together. They interact so strongly that two of them merge or scatter, combining their energy and kicking the third one out with much higher speed. This process is the thermostat that controls the final population. In the searing heat of the early universe, these interactions were constant and frenetic. But as the cosmos expanded and cooled, the density dropped. The SIMP could no longer find enough partners to keep the 3-to-2 process going. The music stopped, and the number of SIMP left standing or frozen out became fixed. This is the so-called SIMP miracle. When theorists calculate the properties needed for this process to work, they find a perfect match. A particle with a mass around that of a proton, interacting via a dark force with a strength we can calculate, naturally produces a leftover density that aligns with the dark matter we observe. It is a self-contained story, a dark matter that creates its own destiny without relying on a connection to our world. This radically different history would leave unique fingerprints on the cosmos. Because SIMP are constantly bouncing off each other, they would act like a fluid with internal pressure. This pressure would resist being squeezed into very small clumps. As a result, a universe dominated by SIMP might have far fewer tiny dwarf galaxies orbiting large ones, smoothing out the small-scale structure of the cosmos in a way that could solve the very same problems that plague the standard cold dark matter model. The hunt for SIMP, therefore, shifts away from trying to catch them bumping into our atoms. Instead, astronomers look for the absence of small satellite galaxies or study the detailed inner structures of dwarf galaxies for signs of this dark matter fluidity. We are searching not for the particle itself, but for the ghostly outline it has pressed into the cosmic landscape. the speed of dark matter might be the key to the universe's structure. While the standard cold dark matter model relies on slow, sluggish particles to build galaxies, another possibility suggests a universe built by particles born in a sprint. This is warm dark matter, a theory that fundamentally changes the timeline of cosmic construction. The defining feature is velocity. In the earliest moments, warm dark matter particles would have been moving at a significant fraction of the speed of light, making them relativistic. This high velocity creates a powerful smoothing effect. Think of trying to build a sandcastle with dry, fast-moving sand. The grains simply will not stick together until they slow down. In the same way, warm dark matter would have streamed freely across the young cosmos, washing away the tiniest gravitational ripples before they could collapse into clumps. It erases the universe's fine details on the smallest scales. This single property offers a potential solution to the nagging missing satellites problem. Our most sophisticated computer simulations based on cold dark matter predict that a galaxy like the Milky Way should be surrounded by hundreds of small, dark satellite galaxies. Our telescopes, however, see only a few dozen. Where are all the missing dwarfs? Warm dark matter provides a clear answer: they were never built in the first place. The relativistic particles prevented those smallest gravitational seeds from ever growing, naturally resulting in a cleaner galactic neighborhood with far fewer tiny satellites. The most promising candidate for this cosmic sprinter is a familiar one, the sterile neutrino, but for it to be warm, it must have a very specific mass. If it were too heavy, it would be cold and slow. If it were too light, it would be hot and would have smoothed out everything, preventing even large galaxies from forming. The sweet spot for a warm sterile neutrino is a mass of a few kilo-electronvolts, billions of times lighter than an electron, but still possessing enough heft to form the large-scale cosmic web we observe. This specific mass range is crucial, as it allows the particles to slow down from their relativistic speeds at just the right moment in cosmic history, permitting galaxies to form while still suppressing the countless smallest structures. The evidence for this idea is written in the faintest, most ancient light and in the distribution of the smallest galaxies we can find. Astronomers are now using the power of the James Webb Space Telescope to peer back at the first galaxies, looking for a telltale delay in their formation. If warm dark matter is real, the very first stars should have ignited a little later than in the cold dark matter scenario, as the universe waited for the particles to slow from their cosmic dash. We are searching for a ghost not by its presence, but by the specific empty spaces it left behind in the early universe. While WIMP were forged in the early universe's thermal bath, another idea suggests a ghost born in the cold. Feebly interacting massive particles, or FIMP, are the spectral opposite of their famous cousins. Where WIMP were once in intimate thermal contact with everything else and then froze out, FIMP were never in equilibrium at all. They were outsiders from the very beginning, barely noticing the searing hot plasma of the Big Bang. Their creation story is one of profound isolation, a process known as the freeze-in mechanism. Picture the early universe as a frantic, crowded party of standard model particles, constantly colliding and exchanging energy. In the rarest of these collisions, a tiny, almost impossible trickle of energy would congeal into a single FIMP. This was not an annihilation or a decay, but a slow, steady dripping of these particles into existence from the chaotic background noise of the cosmos. Because their interaction was so incredibly feeble, once a FIMP was created, it would almost never find another particle to bump into. It would simply drift away into the expanding darkness forever. The population of FIMP was not set by a dramatic freeze-out, but by this slow, persistent drizzle that eventually filled the universe with its gravitational weight. This feeble nature is both the theory's greatest strength and its most daunting challenge. It elegantly explains why we have not found dark matter in our most sensitive detectors. A FIMP interaction with normal matter is so weak it makes the search for WIMP look easy. You could build a detector the size of a planet and wait for 1 billion years, and you might never register a single FIMP collision. They are the ultimate cosmic phantoms, not just dark, but almost completely disconnected from our world of light and matter. Yet, this very elusiveness makes them a compelling and viable alternative. They do not require the elegant but unproven symmetries of supersymmetry. They simply exist in the quietest possible way, their presence only felt by the collective pull of their vast numbers. The universe may not be filled with dark matter that shouts, but with a substance that only whispers, a silent majority created one painstaking particle at a time. The weight of a single particle could have torn the universe apart before it even began. This is the essence of the hierarchy problem, a deep crack in the foundation of modern physics. The culprit is the Higgs boson, the particle that gives all others their mass. According to our best equations, the Higgs should be interacting with the frenetic quantum foam that fills empty space. This interaction should act like a relentless amplifier, driving the Higgs mass to an unimaginable scale, a value quadrillions of times heavier than what we actually observe. At that colossal weight, the fundamental forces would not have united, atoms could not have formed, and life would have been impossible. Our existence is proof that something is suppressing the Higgs mass, taming the wild quantum fluctuations. For decades, this has been physics' most glaring unanswered question. The solution might be hidden in the same place as our dark matter. Certain dark matter candidates, particularly the WIMP predicted by supersymmetry, offer a breathtakingly elegant fix. In a supersymmetric universe, every known particle has a superpartner. The quantum frenzy that wants to inflate the Higgs mass involves contributions from all these particles. But here is the beautiful part: for every particle that pushes the Higgs mass upward, its superpartner pulls it downward with exactly equal and opposite force. They are locked in a perfect cosmic cancellation. The result is a delicate, stable Higgs mass that allows our reality to exist. This is not a convenient add-on, it is a fundamental prediction of the theory. The same mathematical structure that gives us a perfect dark matter candidate also resolves our most troubling theoretical instability. It means the hunt for dark matter is about more than just finding missing mass. It is a search for the cosmic balancers, the hidden particles that keep our entire universe from flying apart at the seams. The fact that the right mass scale for these WIMP to be dark matter is also the right scale to solve the hierarchy problem feels less like a coincidence and more like a profound clue. We are not just chasing ghosts, we are searching for the silent guardians of reality itself. Perhaps we have been overlooking the most obvious hiding place. The search for dark matter has pushed us toward the exotic and the invisible. But what if a portion of the answer has been ordinary matter, simply cloaked by its own cosmic dimness? This leads us to a provocative reconsideration, the theory of baryonic dark matter in failed galaxies. We must revisit the possibility that the stuff of stars and planets could be the ghost we are chasing, not as black holes or dim stars, but as a pervasive, unseen fog of primordial gas. Imagine vast, dark halos not of unknown particles, but of cold, neutral hydrogen, the fundamental fuel of star formation. These would be the corpses of galaxies that never were, immense reservoirs of gas that lack the density or the trigger to ever collapse and ignite into stellar fire. They are the universe's greatest unrealized potential, floating in the darkness between the stars we see. This gas is not completely invisible, but it is incredibly faint. To emit or absorb light, hydrogen atoms need their electrons to be excited, jostled by energy from nearby stars or cosmic events. In the deep, quiet isolation of a galactic halo, far from any stellar radiation, the gas becomes cold and inert, its atoms sitting in their lowest energy state. It is a silent, frozen ocean, detectable only under the most specific conditions. The primary method for finding this cold hydrogen relies on a specific, subtle transition in the atom itself. When the spin of an electron flips relative to the spin of the proton in the nucleus, it releases a tiny amount of energy as a radio wave with a wavelength of 21 centimeters. This is the cosmic fingerprint of neutral hydrogen, but in these failed galaxies, the signal is so weak, so diffuse, that it blurs into the background noise of the cosmos, like trying to hear a single whisper in a roaring stadium. This is where our next generation of eyes on the cosmos comes in. Instruments like the Square Kilometre Array, a colossal network of radio telescopes spanning 2 continents, are being built with this exact purpose. Their unprecedented sensitivity and resolution will act as a cosmic hearing aid, allowing us to tune into the faintest 21-centimeter whispers from the dark halos of galaxies. They will scan the skies not for bright points of light, but for the subtle, ethereal glow of this cold hydrogen fog. The implications are staggering. If these vast reservoirs of ordinary baryonic gas are found, they could account for a significant fraction of the missing mass, especially in the halos of spiral galaxies where the rotation curve problem is most acute. It would mean that a portion of the universe's darkness is not a mystery of new physics, but a testament to the sheer scale and quiet emptiness of space, a place where ordinary matter can simply hide in plain sight, too cold and too spread out for us to have noticed until now. We are on the verge of discovering if the cosmic shadows are filled with the ghosts of galaxies that never woke up. The fabric of the universe might be wrinkled. Imagine the cosmos cooling from its initial unimaginable heat. As it expands and the temperature plummets, the fundamental fields that fill all of space undergo dramatic shifts, much like water freezing into ice. But this cosmic freezing is not always perfectly smooth. In some places, the fields get stuck, locked into a different configuration than their neighbors. Where these mismatched regions meet, a stable, persistent flaw is born in the very structure of reality. These are not particles but topological defects, and their gravitational shadow could be the dark matter we have been searching for. These cosmic scars come in different shapes, each a unique kind of crack in the cosmos. One-dimensional flaws are cosmic strings, unimaginably thin threads of concentrated energy thinner than a proton but stretching across the entire universe with the mass of a mountain range in every inch. A single string vibrating through our galaxy would create a gravitational wake that tugs on stars and gas. Then there are two-dimensional defects, domain walls. These are vast, sheet-like structures, membranes of pure energy separating entire domains of space where a field points in a different direction. A domain wall passing through the solar system would create a gravitational anomaly so severe we could not miss it, warping the orbits of every planet. The most exotic are textures, three-dimensional knots in the fields that slowly unwind over cosmic time, releasing their energy as gravitational waves. The key to this theory is that these defects are not made of matter, they are made of space itself, twisted and knotted in a stable configuration. They are not something in the universe, they are a feature of the universe, as permanent and fundamental as the dimensions of space and time. Their immense mass density comes purely from the trapped energy of the misaligned field, and they interact with normal matter only through their fierce gravitational pull. So how do we hunt for a crack in reality? For cosmic strings, the most promising method involves their effect on the oldest light in the universe, the cosmic microwave background. A string with its immense density would act as a gravitational lens, creating telltale, linear tears in this background radiation. Astronomers meticulously scan this cosmic wallpaper, searching for these faint, straight scratches across the sky. Another method listens for the vibrations of the strings themselves. A large, oscillating loop of cosmic string would be a powerful source of low-frequency gravitational waves, a constant hum in the fabric of spacetime that new observatories are now poised to hear. The search for domain walls is even more dramatic, as their passage would be a singular, universe-altering event. If our galaxy were to pass through one, the sudden change in gravity would be detectable as a simultaneous shift in the timing of pulsars across the sky, a synchronized glitch in the cosmos's most reliable clocks. The profound implication is that dark matter may not be a substance we can isolate in a lab. It could be the cosmic equivalent of the creaks and groans in an old house, the permanent wrinkles in space-time left over from its fiery and turbulent youth. We are not searching for a ghost, but for the fossilized memory of the universe's first and most dramatic growing pains. Gravity may not be a fundamental force at all, but a cosmic mirage. This is the radical heart of Eric Verland's theory of emergent gravity, a concept that pulls the rug out from under centuries of physics. Instead of being a primary ingredient of the universe, gravity, in this view, is a side effect. It emerges from something far more fundamental, the quantum entanglement of the microscopic bits that make up spacetime itself. Think of the universe not as a stage where gravity acts, but as a vast, dynamic network of information. Each particle, each star, each galaxy carries with it a certain quantum information content. When you have a large collection of matter, like a galaxy, the way these microscopic components are entangled with each other changes the very fabric of space in their vicinity. It creates a kind of elastic response, a pushback against the vacuum. Verland's mathematics show that this elastic response to the presence of ordinary matter perfectly reproduces the extra gravitational pull we have been attributing to dark matter. In this paradigm, the dark matter halo of a galaxy is not a cloud of invisible particles. It is a manifestation of the galaxy's own quantum information content warping the space around it. The stars on the outskirts are not being held in by an unseen ghost, but are responding to this emergent property of space, which becomes stronger where the entropy or disorder associated with the visible matter is greatest. This idea does not just tweak the laws of physics, it inverts them. For Verland, dark matter is an illusion, a misreading of gravity's true, emergent nature. The theory's most compelling success is its ability to accurately predict the rotation speeds of galaxies using only the distribution of their visible stars and gas, with no free parameters or dark matter inputs. It is a masterstroke of theoretical economy, solving the puzzle by declaring the missing piece was never missing at all. Yet, for all its elegance, emergent gravity faces monumental challenges. Can it explain the gravitational lensing we see in systems like the Bullet cluster, where the gravity appears divorced from the visible matter? Proponents suggest that the theory's concept of apparent dark mass could still apply, but the calculations are complex and hotly debated. The theory places the universe's heaviest burden not on a new particle, but on a new understanding of reality itself, suggesting that the force that shapes the cosmos is born from the silent, ceaseless exchange of quantum information in the void. The silent tug of dark matter could be hiding a violent end. If this ghostly substance is truly made of particles and their own antiparticles, then a single, chance encounter in the void could be catastrophic. When matter meets antimatter, they annihilate in a flash of pure energy, vanishing into a burst of gamma rays, neutrinos, and other familiar particles. This possibility transforms the hunt from listening for a whisper to scanning the skies for a scream. For decades, scientists have pursued this strategy, known as indirect detection, searching for the final, fiery signature of dark matter annihilating itself. The logic is beautifully simple. Where dark matter is most densely packed, these chance collisions should be most frequent. So astronomers point their most sensitive telescopes toward the places where gravity has corralled the greatest number of these ghosts, the hearts of galaxies and the vast, invisible halos that surround them. The most promising target of all is the turbulent core of our own Milky Way. There, in the chaotic region surrounding the supermassive black hole, the density of dark matter is thought to be immense. If annihilation is happening anywhere, it should be there. And for years, the data from NASA Fermi Gamma Ray Space Telescope has held a tantalizing yet stubbornly ambiguous clue. It is called the galactic center excess. This is a faint but persistent glow of gamma rays, a specific energy of light emanating from the galactic center with no clear explanation. It is not coming from known pulsars, nor from the furious processes around the black hole itself. The distribution and energy of this light perfectly match what many models predict for the annihilation of certain dark matter particles like WIMPs. It is the exact kind of ghostly beacon we have been hoping to find. Yet, the universe loves to complicate things. The galactic center is a messy, crowded place, filled with other potential sources for this emission, like a dense population of unresolved millisecond pulsars, the spinning corpses of dead stars. Distinguishing a smooth, diffuse dark matter signal from the combined flicker of thousands of these tiny, distant lighthouses has proven incredibly difficult. The debate over this gamma ray excess is a microcosm of the entire dark matter hunt. Is it the first direct evidence of the universe's dominant substance meeting its end, or is it just a cosmic mirage, a trick of astrophysical foregrounds? The answer remains locked in the data, a faint light in the darkness that could either be our first real glimpse of the ghost or just another shadow on the cave wall. Our universe might be just one possibility among an infinite array of others. This perspective leads us to a theory that reframes the entire dark matter mystery, not as a puzzle to be solved by a single equation, but as a cosmic accident. The amount of dark matter in our cosmos and its strange refusal to interact with light might not be a fundamental law of physics. It could simply be a random roll of the dice in our particular pocket of a vast multiverse. In this breathtaking vision, countless other universes exist, each with its own unique set of physical constants and laws. In some, dark matter might be far more abundant, causing galaxies to collapse into black holes before stars could ever form. In others, it might be virtually absent, leaving matter too spread out to ever coalesce into galaxies at all. Our universe occupies a very special, very narrow sweet spot. We live in a cosmos where the density of dark matter is just right, enough to provide the gravitational scaffolding for galaxies to form and evolve over billions of years, but not so much that it smothers the birth of stars and planets. This is the essence of the anthropic principle, a logical but deeply controversial idea. It suggests that we should not be surprised to find ourselves in a universe capable of supporting life, because in all the lifeless universes there is no one to ask the question. The profound difference between dark matter and ordinary matter, then, might not be the result of a deep, underlying symmetry. It could be a local byproduct, a random combination of fields and forces that happen to freeze into existence in our particular cosmic bubble. The ghostly nature of dark matter, its refusal to interact, might be the very reason we are here to notice it. A dark matter that interacted strongly with light or atoms could have heated the primordial gas, preventing the delicate collapse into the first stars, or it could have clumped too densely, disrupting the formation of planetary systems. In this view, the silence in our detectors is not a failure. It is the expected background condition of a universe that won the cosmic lottery. We are not searching for a missing piece of a perfect puzzle, but studying the unique and perhaps accidental properties of our own cosmic home, one that just happened to have the right kind of ghost to build a world upon. The information swallowed by a black hole might not vanish without a trace. For decades, physicists have grappled with the black hole information paradox, a conflict between quantum mechanics and general relativity that suggests the universe forgets. Anything that falls into a black hole, from a star to a single particle, carries information, a unique configuration of matter and energy. Quantum law states this information can never be truly destroyed. Yet, if a black hole eventually evaporates through Hawking radiation, what happens to all that data? the paradox implies it is erased, a violation so profound it threatens our understanding of reality itself. A radical solution now suggests that dark matter could be the universe's ultimate backup drive. The theory proposes that the information consumed by a black hole is not lost inside the event horizon. Instead, it is imprinted or encoded onto a halo of exotic particles that form a gravitational corona around the black hole. These particles are not made of ordinary stuff. They are the physical manifestation of the information itself, translated from the doomed matter into a stable, quantum gravitational form. This halo would be a perfect candidate for dark matter, invisible and interacting only through gravity, a permanent record of everything the black hole has ever consumed. Think of a black hole not as a cosmic shredder but as a sculptor. When a star is pulled in, its immense mass and energy are converted. According to this idea, the information that defined that star, its composition, its spin, its very identity, is not erased but remade. It is transformed into a new kind of particle that takes its place in the surrounding halo. This process would be a fundamental mechanism of quantum gravity, a way for the universe to preserve its memory without breaking its own rules. The dark matter halo becomes a living archive, a library of cosmic history written in a language of mass and gravity. This speculative bridge connects two of the greatest mysteries in science. It offers a potential origin for dark matter that is not from the Big Bang's thermal bath, but from the ongoing, dynamic evolution of the cosmos. Every supermassive black hole at the center of a galaxy could be surrounded by a vast, information-rich cloud of dark matter, the accumulated record of its galactic feasts. This would mean the ghostly substance shaping the cosmos is in essence the preserved memory of everything that has ever fallen into the abyss. We are left with a hauntingly beautiful possibility. The invisible weight guiding the stars might be the universe's way of remembering, a silent testament written in the language of gravity, ensuring that nothing, not even a black hole's appetite, can make the cosmos forget. The nature of reality itself might be the ultimate container for our mystery. Venture into the most speculative realm where dark matter is not a substance but a symptom of a deeper truth, the idea that our universe is a sophisticated simulation. From this philosophical perspective, the ghostly presence we call dark matter could be the underlying computational framework. It might represent the memory and processing power required to render the cosmos in real time. Think of the universe as an unfathomably complex video game. The stars, the planets, the atoms you are made of, these are the graphics, the rendered output you see on the screen. But every simulation requires a backbone, a substrate of code and processing cycles that remains hidden from the user. Dark matter, in this view, is that hidden substrate. Its gravitational influence is the detectable signal of the simulation's operating system working in the background, allocating resources and calculating the physics that holds the virtual world together. Why does it not interact with light? For the same reason the code of a game does not appear within the game world itself. It exists on a separate layer of reality. This is not a scientific theory that can be tested with our current tools, but a powerful thought experiment that reframes our entire search. It highlights the sheer depth of the mystery. We have been trying to find a particle or a force, but we might be looking for the architecture of the system we are running on. The profound silence from our detectors, the way dark matter seems to be everywhere yet completely intangible, could be a clue that we are probing the limits of our own reality. If this is true, then the dominant component of the cosmos is not a physical thing, but the literal fabric of the simulation, the cosmic computer's hardware made manifest as gravity. It transforms our quest from a hunt for a ghost to a question about the nature of existence. Are we searching for a missing piece of the universe, or are we merely beginning to sense the edges of the simulation we call home? So we return to the most radical possibility of all, that the ghost we have been chasing does not exist. The final theory brings us full circle, suggesting dark matter is a grand illusion, a persistent error born from our fundamental misunderstanding of gravity itself. We have already explored the bold proposals of modified Newtonian dynamics and emergent gravity, ideas that rewrite the rules of the cosmos to erase the need for invisible mass. Their appeal is powerful, a stunning elegance that solves the puzzle of galaxy rotations with breathtaking precision, using only the stars and gas we can actually see. It is a vision of a simpler, more transparent universe, yet this beautiful idea crashes against the hard rocks of cosmological evidence. The most famous challenge is the Bullet Cluster, a cosmic collision of two galaxy clusters that presents a profound visual riddle. Observations show that the hot gas, the dominant visible mass, was slowed and tangled in the collision, but the gravitational mass mapped by the bending of light from background galaxies sailed right through the wreckage. The gravity is not where the visible matter is. This is exactly what you would expect if dark matter were a collisionless substance, a ghost that ignores normal matter and simply passes through. For modified gravity theories, this is a devastating puzzle. If gravity is tied directly to visible mass, how can the strongest gravitational pull be in the empty space between the gas clouds? Proponents have worked to explain this within their frameworks, suggesting that perhaps the residual neutrinos in the clusters could account for the effect, but these solutions feel strained, adding back the very kind of unseen matter the theory sought to eliminate. The evidence does not stop there. The intricate cosmic web, the vast filamentary structure of the universe traced out by galaxies, was seeded by tiny density fluctuations in the early cosmos. The pattern of these fluctuations is imprinted on the cosmic microwave background, the oldest light we can see. The characteristics of this pattern, the precise ratios of hot and cold spots, demand the presence of a cold, collisionless substance that makes up about 5 times the mass of ordinary matter. Without this dark component, the universe would not have clumped in the way we observe. The acoustic peaks in this ancient light are a cosmic barcode, and they scan correctly only when dark matter is in the cart. Computer simulations of the universe that include dark matter successfully grow structures that look exactly like our real cosmos, from the largest superclusters to the smallest dwarf galaxies. Simulations that try to use modified gravity alone have, so far, failed to reproduce the rich tapestry we see. The tension at the heart of modern cosmology is now undeniable. On one hand, the rotational curves of individual galaxies cry out for a modified law of gravity, a solution of stunning elegance. On the other, the large-scale structure of the universe and the forensic evidence from cosmic collisions scream for the existence of a mysterious, unseen substance. So where does this leave us? Perhaps the answer is not a choice between these two paths, but a synthesis we have not yet imagined. Maybe gravity is indeed more complex than Einstein dreamed, and dark matter is also real, a substance far stranger than the simple WIMP we first envisioned. The ghost may be real, but its reflection in the laws of physics may be more complex than we ever guessed. From ghostly particles to cosmic superfluids and cracks in spacetime, we have journeyed through a universe of possibilities. This incredible diversity of thought is not a sign of confusion, but a testament to the vibrant, creative process of science itself. Each theory, from the heavyweight WIMP to the wave-like Axions, from the shadow universe of mirror matter to the radical rewrite of gravity, represents a different path forged by human curiosity. They are all maps drawn to navigate the same vast, uncharted territory. The silence from our detectors and the puzzles in our data are not failures, they are guideposts telling us the answer is more profound than we first imagined. This mystery remains one of the grandest in all of human knowledge, a cosmic riddle that has resisted solution for decades. It reminds us that the universe is under no obligation to be simple or to conform to our expectations. The true nature of dark matter is still out there, waiting in the dark, and the next great discovery could come from a deep underground lab, a revolutionary telescope, or a single, brilliant insight that reconfigures our entire understanding of reality? So we turn this final question over to you. After this tour of the cosmos's greatest ghost, which of these 30 paths resonates most deeply with your own sense of wonder? Do you find the elegant simplicity of modified gravity compelling, or does the idea of an entire hidden sector, teeming with dark photons and dark chemistry, capture your imagination? Share your favorite theory in the comments below and let us know which cosmic mystery we should explore next. Remember to subscribe and join us as we continue our journey to the very edges of the known.